Problem 18.31. A random sample of 500 car batteries revealed the following distribution of battery life. For these data, the sample mean is 2.8 and the sample standard deviation 0.97. At the 5% level of significance, does battery life follow a normal distribution? Okay, so we've got some data. It's already been summarized into a frequency distribution. We're wanting to do a hypothesis test, and the test we're wanting to do is to see whether the data is normally distributed. Remember, when we're wanting to see if data follows a particular distribution, we can use the goodness of fit hypothesis test. Now, it's a hypothesis test, so we need to still set up the null and alternative hypotheses. We need to come up with a decision diagram, then we can calculate a test statistic and make our decision. Now, the trick with a goodness of fit test is that the null hypothesis is always that the data follows the particular distribution we're testing. Now remember, there are an infinite number of normal distributions, and so you have to specify which individual normal distribution we're looking to see if the data follows. So we can use our sample mean and sample standard deviation as our parameters. So the null becomes the distribution of battery life is normal with mean 2.8 and standard deviation 0.97. That's the normal distribution we're going to test our data for. If the null is that it follows that distribution, then the alternative is that the data does not follow that distribution. So that's how we always set up the null and the alternative. And we can also just make a note that our alpha is 5%, which is just 0.05 as a decimal. Now, the goodness of fit test is based on a chi-squared distribution. So the next step is to draw up the decision diagram. We draw up our chi-squared distribution. Now remember, a goodness of fit test is one of our special hypotheses tests where we always have the upper tail reject region, and that's going to relate to the logic behind the test statistic, which we'll talk about in just a moment. So with the goodness of fit test, it is always an upper tail reject region. So our upper tail reject region will be 5% in size. The chi-squared distribution has degrees of freedom, and for this test it will be k minus p minus 1 degrees of freedom. K is the number of categories or classes, p is the number of parameters, and for a normal distribution that will always be 2, and then it's just the minus 1. So you can see back in the frequency distribution that we have 6 classes that we're looking at. So k is 6, p is 2, that gives us 3 degrees of freedom. Now if you look up the 3 degrees of freedom row in the chi-squared table and then to the column for an upper tail of 5%, you'll see that the cutoff is 7.8147. So that's our cutoff point for the upper tail reject region. So now that we've got our decision diagram, we can process the actual data and have a look at calculating the test statistic. Okay, so I've redrawn the frequency distribution at the top of the page, and you can see I've created 2 more columns, the probability column and then the expected frequency column. Now the way the test statistic works for this hypothesis test is we've got to compare what we've observed, so the data that we've observed, to what we'd expect if it was normally distributed with mean 2.8 and standard deviation 0.97. So it's quite similar in that respect to our test for independence. The test logic is the same. We've got some data we've observed, we're going to compare it to what we'd expect to get if the null hypothesis was true. Now we've got our frequency, we're processing this data on the basis of the classes, so we're not just looking at the individual values, we've grouped them into classes. We've got 6 classes, we've got that frequency column, that's the sample data. Now we need to be able to compare those observed frequencies to our expected frequencies, expected on the basis of the null being true. Now, before we can get to the expected frequencies, we've got to firstly work out the corresponding probability for if the null was true. So we need to say, well, if it is this normal distribution, what do we expect to get in the first class, in the second class, and so on. So you've got to start off with saying what do we expect in terms of a probability, and then we can convert it to an actual count because we've surveyed 500 bits of data, so we can apply our probability to 500 to come up with an actual expected frequency. Now, these do take a lot of work in terms of putting everything into your calculator. I've got the steps and we'll talk through the first class, and then you apply the same procedure to all of the remaining classes. So for example, if we look at the first class, we've got between 0 and 1 years. So we say, okay, well, if the data was normally distributed with mean 2.8 and standard deviation 0.97, what are the odds that we get a value in the class between 0 and 1? So that's an X probability. What's the probability that X is between 0 and 1? That normal distribution we don't have a table for, so we must convert it to a corresponding Z distribution or an equivalent Z distribution so that we can use our Z tables to solve. So the 0 and the 1 as X values, we've got to convert them to equivalent Z values. So how do we do that? Well, we make a Z-score. You look at the X value, 0, you subtract the mean, 2.8, divide by standard deviation, 0.97. Remember, when we do a hypothesis test, we proceed on the basis that the null is true. If the null is true, the mean is 2.8 and the standard deviation is 0.97. We do the same for our upper boundary of the class, 1, subtract the mean, divide by standard deviation. That tells us that the probability of getting a data value in the class 0 to 1 is the same as finding the probability that Z is between negative 2.88 and negative 1.86. Once you've got it to that point, it's just a Z probability problem, and you can solve that using our tables, and we come up with a probability of 0.0294. So that's the probability of getting a value in that class if the data is normally distributed with mean 2.8 and standard deviation 0.97. The probability is a good starting point, but we have to have the expected frequency. We have to go from that probability and say, well, if that's the probability, how many of the 500 values that I surveyed should have been in that class? So to get the expected frequency and therefore answer that question, we can just multiply the probability by the sample size. If we do 0.0294 times 500, we get 14.7. So what this is saying to us is that we've observed 12 values in that class when we took the sample. If it had been normally distributed data, we should have got 14.7 values in that class. So that's what we're going to compare as the basis of the test statistic. So what that means is to finish off the remaining 5 classes, you've got to get the probability of getting a value in that class if the null is true, and then you go from the probability to the expected frequency given you've surveyed 500 values. You can see I've got all the values there for you to check. Once you've got the second column, which was in the question, and that final expected frequency column, so you've got your observed and your expected, we can calculate the test statistic. Now the logic is you look at the difference, you square it, divide by the expected to make it relative, and then you add that up over all the classes. So for example, the first component is 12 minus 14.7, you square that, then divide by 14.7. Our next class, we observed 94, we expected 87.4. So you do the same calculation. You do that for every class and then you add them all together. We come up with a test statistic of 19.36. So our test statistic is clearly in the reject region. So we say let's reject the null. We can say there is sufficient evidence to conclude that the distribution of battery life does not follow a normal distribution with mean 2.8 and standard deviation 0.97.